Good afternoon, everybody. Welcome to another exciting afternoon at Chem 170 with your host, me, Dr. White. Hi, hope you all had a good time since we last met. I got a lot done. Whoa, did I get a lot done? Which is always a good thing. And thank you for turning on your webcam. All right, important things. First of all, I saw a lot of you have already looked at my video of the method, how to eliminate test anxiety. Important note, once you've got your memory and practice it, bring it back. Remember what you saw, what you heard, and everything. It's in the video. And if you don't get a big smile when you bring back that memory, you need a stronger memory. And also, don't forget, come to my office hours, say after class, or email me and I can set up a special meeting on Zoom and I can check, do you have a good memory and will the method work for you? Only takes a minute, a couple minutes, and I've been doing this for a long time. All right, that's number one. I got my list of things to do here. The other thing, don't forget the lab we did last Wednesday. I like those special effects. Awful. But anyways, the lab we did last Wednesday is due this Wednesday by the end of the day. So don't forget to upload the answers to the questions. If you don't have a printer, just write out the answers on a piece of paper. You don't have to put the questions down when you do that. And then with your cell phone, take a picture and upload it as a single PDF file. If you look in lab number 1, I have instructions, different ways to make a single PDF file from pictures you take with your cell phone. All right. Well, in that case, let's get back to organic chemistry. Oh, notice the red spot from doing this too much? Not really. But anyways, any of you happen to think of a gas, alkynes, when you went by a gas station? Wait, maybe you happen to think of double bonds if you saw a carrot or a tomato, or if you smell the lemon. Remember, organic chemistry is all around you. I stole that from SpongeBob. And it won't hurt for you to think about it. Or not in lecture if you're not watching my videos, which I see a lot of you have been watching my videos. So thank you. You're making me a YouTube star. All right, let's get to work. All right, on Wednesday, I was discussing reactions of alkynes. Alkynes are, oops, I gotta turn on my, hold on one sec. I didn't turn on my tablet. Now it's on. We're talking about alkynes, a carbon-carbon triple bond, 3 lines. Remember, it has 2 pi bonds. There's something you should know, and 1 sigma bond. And as you've learned from double bonds, pi bonds, I can break like that, and I do. And here last week, we ended up where I talked about, and you did some practice, where hydrogenation of a triple bond. And just to remind you, triple bond, 2 pi bonds, 1 sigma bond. You take hydrogen gas, and remember, organic chemists are lazy. We don't want to balance a chemical equation a lot of times, so we'll use this bracket, the letters X and S, closed bracket means excess. All the hydrogen in the world that will react with anything, hydrogen reactive. And you need a catalyst, and that's nickel, platinum, or palladium. And when you break each pi bond, each carbon gets a hydrogen. Well, 2 pi bonds each carbon of the triple bond gets 2 hydrogens. And since we already went through this, I'm going to let you do this one. See what a nice person I am? I share all the fun. And a question would be 3 points each. Give the organic product or products are the following. Your turn. And for those of you who haven't, if you want to turn on your webcam, it makes Dr. White happy because I can see real people. Thank you, Louise. And we'll wait for everybody to finish. Don't forget the vote. So I know you finished. We were face to face. I could look around the classroom and see everybody had their webcam on. I could look around the webcams and see too. All right, my turn. When you look at an organic molecule, you should look for what's different. What's not a carbon-carbon single bond or carbon or hydrogen atom should get your attention like that. Hopefully that got your attention. And if we look at this molecule, and by the way, when I look at an organic molecule, when I'm doing work, I consult or work on my own projects, I look at what's different immediately. And here we have a triple bond. Everything else is carbon, hydrogen, carbon, carbon single bonds. That's just going to come along for the ride. The triple bond is where the action is and the fun. And we're reacting that triple bond with excess hydrogen. Excess means you have all the hydrogen in the world, anything that react with hydrogen. And we have a catalyst. And that catalyst is palladium. And it could have been nickel or platinum, but as I said, it's palladium. Remember, this has 2 pi bonds, 1 sigma bond. You break each pi bond, and each carbon of the triple bond gets 2 hydrogens, 1 for each pi bond. Do you break carbon-carbon single bonds? No. Hold on, I better do this right. No, you don't. And therefore, we have 1, 2, 3, 4, 5, 6 across. 1, 2, 3, 4, 5, 6 across. Methyl here and 2 methyls here, which are my 2 carbons of the triple bond. I broke the 2 pi bonds. That's why there's only 1 line or bond between it. Remember, each line is a pair of electrons, and each one of these gets 2 hydrogens. I know there are 4 bonds to carbon, so I can put in the rest of the hydrogens. And remember, it's your solemn responsibility that if I make a mistake, especially putting in hydrogens, let me know immediately so I can correct it. And that's how you do it. And like I said, we did some of these on last Wednesday. So it's time to move on. Now, another important reaction of triple bonds is halogenation. And here, remember, triple bond, 2 pi bonds, 1 sigma bond. And again, we're using the term XS, or the abbreviation bracket, the letters XS, close bracket, to show we have all the halogen gas. Remember, X is the abbreviation, or I should say the variable organic chemists use for either the halogens fluorine, chlorine, bromine, or iodine. And you break each pi bond, and each carbon of the triple bond gets not 1, but 2 halogens. By the way, this is Cl, chlorine. I've given up on trying to just print out Cl. It doesn't look good. And remember, this has 2 pi bonds and 1 sigma bond. And when you break each pi bond, each carbon of what was the triple bond gets 2 halogens. And if we look at the following reaction, what's the product or products? Look for what's different, what's not a carbon single bond or carbon or hydrogen atom. Should get your attention like that. Hopefully it did. And we have a triple bond. We're reacting with fluorine gas. Oops, I've forgotten. I do this once in a while. The excess. At my level, we don't even put that down because you know if you need it, it's there. But anyways, this is a halogen. Remember, X can be fluorine, which it is, chlorine, bromine, or iodine. And since you have 2 pi bonds, you break them, not the sigma bond, and each carbon of the triple bond gets 2 halogens. Do you break carbon-carbon single bonds? No. I have 4 carbons in my starting material or starting reactant. And here are my 2 carbons of the triple bond, these 2. Notice I broke the 2 pi bonds. Each one gets 2 halogens. In this case, it's fluorine. I know there are 4 bonds to carbon, so I can put in the remaining hydrogens. Now, why do you want to put a lot of halogens on a molecule? Well, it makes it more flame retardant. Nothing is flame proof. Anything that can burn, eventually you can heat it up, it will burn. The other thing, putting a lot of halogens in a molecule makes it more stable to heat, not only just burning. And they don't do it now, they've gone to other ones, but the next time you're out driving and you see one of those power stations, ComEd in Northern Illinois uses, and elsewhere in the United States, where, hold on, let me see if I can find a picture. All right, does everybody see the substation transformer on your screen? Thank you. You notice right here, you got a fan, and in here, these are transformers. which change high voltage power lines to lower voltage and eventually so you can use it in your home. Well, when you do that, that gives off a lot of heat, which is not good for the transformers. And besides having fans right here that cool it, they have liquid circulating in there and surrounding the metal in the transformers. And that liquid, it's not water, is a very high boiling, stable material. And for a long time, it used to be poly. The word poly means a lot, halogenated organic compounds. Now, the bad thing about polyhydrogen halogenated compounds, some of them are very carcinogenic. They cause cancer. So they've been changed to the other ones, and I'm not sure what they're using. I have really looked into it. That's not my area. I practice organic chemistry in it. Anyways, it's always good to know, why am I learning this? All right. And here's one for you to do. Give the organic product or products for the following reaction. Remember, these general reactions that I'm teaching you, hopefully you're memorizing them. Oh, I almost forgot. Once we're done with this, I'll talk about it. And again, this is the beauty, and it really is beauty and the power of general reactions. No matter what the molecule, you have that functional group, 99% of the time, it will react the way I show you. That 1%, we're talking about people like me who have to deal with, you won't. All right, I think everybody's done. So it's my turn. If we look at this molecule, what's different? A triple bond. Remember, that has 2 pi bonds and 1 sigma bond. And a triple bond, what are we reacting with? Chlorine gas. A halogen, we have excess. And in bracket XS, the letters, close bracket says you have all the amount of that gas, halogen gas, you need to react whatever it will react with. In this case, it's the triple bond. Again, 2 pi bonds, 1 sigma bond. Each line is a pair of electrons. And you break the 2 pi bonds, and each carbon of the triple bond gets not 1, but 2 halogens. And you break carbon-carbon single bonds. No. So I have 3 carbons. I better end up with 3 carbons. Here are my 2 carbons of the triple bond. Each one gets 2 halogens, in this case chlorine. And I know there's 4 bonds to carbon, 4. Anybody having nightmares seeing me go, how many bonds to carbon? 4. And remember, each halogen counts as a bond. I'm done. And we've made that tetra, meaning 4 chloro. And I'll teach you this next chapter, after we're through with this one, about how to name halogens on a molecule. Oh, let's do another one. These are fun. And here's another one for you to have fun with. Give the organic product or products 3 points each. And thanks to all of you who are answering my poll. That way I know when you're done. All right, looks like everybody's done. Let's do this. How do you determine what are the product or products for this reaction? You look for what's different, what's not a carbon-carbon single bond or carbon or hydrogen atom should get your attention. And woo, this got my attention, a triple bond. Everything else is going to come along for the ride. And what do we have? Br, bromine is a halogen. Organic chemists use X to denote halogen. Halogen gas exists as diatomic molecule, X2. And notice we have excess. And that means you have all the amount of that reagent, in this case, halogen gas, to react whatever it could react with. And just to remember, X can be fluorine, chlorine, or in our case, it's bromine, or it can be iodine. Nasty stuff to work with. Have done this reaction with bromine and chlorine gas. And you break the 2 pi bonds in the triple bond, not the sigma bond, and each carbon of the triple bond gets not 1, but 2 halogens. Now, do you break carbon-carbon single bonds? No, so I have 1, 2, 3, 4, 5, 6 across. On this carbon, I have an isopropyl group. On this carbon, I have a methyl group. Here are my 2 carbons of the triple bond. I broke the 2 pi bonds, and each one gets not 1, but 2 halogens. In this case, it's bromine. And I know there are 4 bonds to carbon. So I can put in the rest of my hydrogens. And there you go. Again, look for what's different. Triple bond reacting with excess bromine. You break the 2 pi bonds, and each carbon of the triple bond gets 2 halogens. And you don't break carbon. No, you don't. You don't break carbon-carbon single bonds. Remember on test 1, 2, 3, and 4, and my final, your 2 friends are, there's 4 bonds to carbon. Do you break carbon-carbon single bonds except for combustion? In my class, no. And once I started teaching that, the grades zoomed way up. And more than teaching it, I hate to say this, but I've been brainwashing you, so it's burned in your brain. Now, this morning, I was thinking about, well, what am I going to lecture? Yeah, I knew, but where should I go? And I realized I forgot to talk about something important with carbon-carbon double bonds. I don't have a slide for it, so I'll do it the old-fashioned way. You have a double bond, react with a halogen gas, you learn, you break the pi bond, that's one pi bond, one sigma bond, and X can be fluorine, chloramine, bromine, or iodine. Now, what I didn't teach you is when you have more than one functional group in a molecule. And let's look at the following molecule. And the question is, what's the organic molecule reaction? Let me start that again. I just had a brain tongue failure. What's the product or products for the following reaction? And if we look at this molecule, there's something different, a double bond. Well, wait, there's a second double bond. Now listen carefully. When a double bond is separated from another double bond by one or more carbons, it reacts just like it was alone. I'll say that again. When a double bond is separated by one or more carbons, each double bond reacts like it was alone. If they're not separated, that's a whole nother case that I could talk about if this were a 2-semester organic, but it's not. So I want to spend more time on other things that are more important, but still this is important. So do you break carbon-carbon single bonds? No. So I have 6 carbons. My first 2 carbons of this double bond, I break the pi bond. Remember the reaction we're doing. You break the pi bond, each one gets a halogen, and the halogen is iodine. And the other double bond, these 2 carbons, you break the double bond, and each one of those gets an iodine. And I put in the hydrogens. And I'm done. So the lesson here is when you have a double bond, it's more than one in a molecule, and they're separated by more than one or more carbons, they react like they're alone. Now, notice here I use the excess because you need 2 moles of iodine, and I'm lazy. I'm an organic chemist. I don't want to balance it, so I do it that way. Your turn. Give the organic product or products for a following reaction. 3 points each. If you haven't figured out, we're doing some high-level organic chemistry now. I should say you are. You should be very proud of yourself. I'm proud of you. All right, let's take a look at this. Look for what's different, what's not a carbon-carbon single bond or carbon or hydrogen should get your attention. Ooh, a double bond, a second one. And what are they're separated by one or more carbon, double bond. Remember, that's one pi bond, one sigma bond, and chlorine gas is a halogen. I have excess. Now, why did I need the excess? Because I have not one, but two double bonds. And you learned without the excess, you break the pi bond. Each carbon gets a halogen. This can be X, the halogen can be fluorine, which in our case is chlorine, bromine, or iodine. And do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5, 6, 7 carbons. Here are my 7 carbons. Here's 2 carbons of the double bond, and here are 2 other carbons. I broke each pi bond, and each one gets a halogen. Remember, double bond, only one halogen per carbon. Oops. And that's chlorine. And it's important you put them on the right carbons of the double bond, or I mark it wrong because it is. And now I'll put in my hydrogens. Remember, each halogen counts as a bond. And there are 4 bonds of carbon. And that's how you do it. Oh, I got to do another one. Let you do another one. And in case you haven't learned the general reactions, I'll help you out. And there's the reaction for you to do. Give the organic product a product of the following. Remember Markovnikov's rule, the carbon of the double bond with the most hydrogen gets the H, the other gets the halogen. And remember, in my class, in my world, there's no such thing as a dumb question. If you ever have any questions, always feel free to ask. You can always send me a private chat if you don't want other people to see you're asking questions, or you can send a public chat, or you can just turn on your mic and ask a question, because I encourage questions. I just did. All right, looks like everybody's done. So if we look at this molecule, look for what's different, what's not a carbon hydrogen atom or a carbon-carbon single bond. I see a double bond. Wait, there's a second double bond. And I'm reacting it with HBr. I have excess, which just says I have all the hydrogen bromide, hydrogen halogen that will react with anything it can. In this case, double bond reacting with HX. You break the pi bond, one carbon gets H, the other gets X, and it follows Markov-Nikolson rule. The carbon of the double bond with the most hydrogens gets the hydrogen, the other carbon gets the halogen. Well, do you break carbon-carbon single bonds? No. I have 5 carbons, I better end up with 5 carbons. My first double bond is here. This has 2, this carbon has 1, which is the greater number, and time's up. Hopefully you pick 2. The hydrogen will go there, the other, the halogen, in this case, bromate. Now over here, I have my second double bond. And this carbon has 2 hydrogens, and this one has 1, which is the greater number, again, is 2. Excuse me. And the hydrogen will go there, and the bromine will go there. And I now know there are 4 bonds to carbon. I've made this dibromo. Di means 2. Bromo is the prefix we use, or the way we say it's a bromine compound. So the key thing is when you have more than one double bond and they're separated by 1 or more carbons, each one reacts like it's alone. Now, before I forget, because I've been forgetting, time for a public service announcement from your host, me, Dr. White. All right, as I sent out an email and posted as an announcement, even though it says in the syllabus, this Wednesday will not be test number 1. I postponed it by a week. It'll be a week from this Wednesday. I could have rushed today and Wednesday too to finish up, and that's not fair to you, and I don't do that. And generally the first test, I'm always off when we start in the spring, because I think, well, I can get a lot done that Wednesday we started, and I don't get as much done as I thought I could. And that's why, remember, test 1 will not be this Wednesday, but a week from this Wednesday. Now, there's another thing I want to talk about now that we've essentially finished this chapter, but something you should be aware of and learn about. No company is ever going to hire an organic chemist or a PhD organic chemist and say, hi, we're hiring you because if I react this and this, what do we get? No, they're not going to pay you money. You could do an undergrad student who's taken organic chemistry. They can do that. No, they're not going to pay money for that. A key thing is, I need to make this product. How do we do that? And at my level, I've been in meetings with, because I've been a senior research and development manager, with the vice president of marketing and sales and some of his top people. And I've been in a meeting and they say, we need to make this type of product that does this for our customers at this price. Now you're at my level. And how do you do that? That's called synthesis. Synthesis is a fancy word meaning to make. And my training in graduate school to get my PhD, and what I did mainly in industry, not all, but most of it, is synthetic organic chemistry. I'm a synthetic organic chemist. I've been trained and I've made new products to help companies make money, which then are used by our customers, including you, such as, we'll talk about it way down the road, fabric softeners. That's an area I worked in. So how do we do this synthesis? And that's the fun part of organic chemistry. I mean it, really the fun part, but I'm biased. I'm a synthetic organic chemist. Well, let's look at synthesis. And this is called the synthesis problem. And the question is, what do you react the question mark with bromine gas to make that molecule? Well, how do you do that? Well, you look for what's different in the product and say, wait, what's not carbon? What's not hydrogen? What's not a carbon-carbon single bond? I've got two adjacent bromines. And I remember, and I'm reacting something with bromine, that's a halogen. Remember, X can be fluorine, chlorine, bromine, or iodine. And you've learned this general reaction. And what do I start with? This is something you have to learn, memorize, a double bond. So if I take a double bond, react with halogen, I'll get two halogens on adjacent carbons. Well, do you break carbon-carbon single bonds? No. So if I end up with 4 carbons, I better start with 4 carbons. Now, the 2 carbons with the halogen are the 2 carbons of my double bond, which would be these 2 carbons. And I know, no, there are 4 bonds to carbon. And that's the answer. If I take this molecule, react it with bromine gas, I will make this product. And that's synthesis. Oh, let's have you try one. And what would you react with iodine to make that molecule? Your turn. It looks like everybody's done. So I better get to work. How do you determine what's the starting material? What's the reactant? Remember, I come from industry. A plus B makes C. These are the starting materials. C is the product. All right. So I look for what's different, what's not carbon. Ooh, what's not hydrogen? I see these two halogens. And they're on adjacent carbons. And I remember halogen is abbreviated by the X. I'm reacting with halogen gas. X equals fluorine, chlorine, bromine, or iodine. And what do you start with? A double bond. Do you break carbon-carbon single bonds? No, not with this reaction. And I end up with 1, 2, 3, 4, 5 carbons. I better start with 5 carbons. I do. Now, here are my 2 carbons with the halogen, which are these 2 carbons, which are these, the carbons with the double bond, which are these 2 carbons. So there has to be a double bond between there. I know there are 4 bonds to carbon. Double bond counts as 2 bonds to each carbon. And that's how you do it. Oh, I got to do another one. I've got to share the fun. I'm going to help you out on this one on a test. I won't. And there you go. Question is what, and we're going to go a couple minutes over into our break, but I'll still give you 5 minutes. I won't cheat you. All right, I think everybody's done. My turn. All right, so how do we determine what do you start react with HCl to make this compound? If I look what's different, ooh, I've got a carbon with a halogen on it. I'm reacting with HX. Remember, X equals chlorine, bromine, or iodine for this reaction. Nobody uses HF, it's too dangerous. And for this reaction, my adjacent carbon to the halogen has a hydrogen. It follows M's rule, Markov-Nichols rule, and we have a double bond. So here's my carbon with the halogen. It's one of the carbons of the double bond. My adjacent carbon with a hydrogen is my other one. Now, do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4. 1, 2, 3, 4, plus 2 methyl groups. Here's the carbon with the halogen, and the only adjacent carbon with a hydrogen is this carbon, and that will have the double bond. If you notice, this carbon at the end has the most hydrogens, so it's got 2. Markov-Nichols rule says the hydrogen from HX will go there. It's now got 3. The other carbon will get the halogen. Now, one of the things I've done with this reaction is the following. What if you said, oh, a carbon with a halogen and adjacent carbon are the carbons that double bond. Here's my carbon with the halogen. Here's an adjacent one. So I'll do this. And say this is the product. Guess what? It's wrong. How do you know immediately it's wrong? There's 5 bonds to carbon. 1, 2, 3, 4, 5. No, that can't happen. If you find a way to get 5 bonds to carbon, let me know. We'll be rich beyond my wildest dreams. And that goes beyond having my own fighter jets, my own Lamborghini and Ferrari, and my own island in the South Pacific. It goes beyond that. It doesn't exist. So the important thing when you're doing synthesis, whatever the problem, look at the product. Look for what's different, what's not a carbon, what's not a hydrogen, what's not a carbon-carbon single bond. Should get your attention like that. You look at the reagent, and then you need to know a general reaction. And how do you learn these? You write them down and say them 5 times. And you may have to do it more than once. I personally don't like flashcards. And all except I did have over the years a couple of students who did well with flashcards, but most people do what I recommend. And one of the things I've been doing secretly in class, under each reaction I show you, I always write the general reaction. That's also helping you learn it. With that, that's synthesis. Now, synthesis is a lot more complicated problem than give the product or products. And at least at this time, the Supreme Court still has outlawed cruel, unusual punishment to students. So on test 1, there'll only be 1 synthesis problem, only 1. And it can be of any of the functional group chemical reactions I show you. Now you say, Dr. White, you don't have that in your problem set. No, I don't need to. Take any regular problem, cover the starting material, look at the answer and say, what would be the starting material? And you've got your synthesis problem. And with that, let's take a break. I'll see you in 5 minutes. I'm gonna get up and stretch. Let's get going. Oh no, nobody has their webcam on. Oh, thank you. And thank you. All right, personal note, about almost a year and a half ago, a little less than that, I had major cataract surgery on both eyes. I used to always wear glasses. If you go back and look at the older YouTube videos, you can see I've got my glasses on. And before I had my cataract surgery, I always bought glasses once I found out about it, instead of from an optometrist, which they rip you off, from Zenny. That's the company I use, and it's quite reasonable. And the reason I'm saying that is, since I had my cataract surgery, and if you need the name of outstanding eye surgeon, Dr. Cabin, and contact information for anybody you know, he's in Hoffman Estates on Barrington Road. But anyways, email me or contact me and I'll share that with you. But anyways, he said you'll need reading glasses now, because I never did before, but because of the cataract surgery, I don't need my regular glasses anymore. But to read like this, yes, I need reading glasses. At this distance to my screen and keyboard, I don't. Well, I had one pair I got from Zenny's, cost me a whole, including shipping. Are you ready for this? $17. And I had gotten to the point where, oh, they're upstairs. I got to go upstairs and get my reading glasses. By the way, say hello to your cat for me. Pets are allowed, so are children in my class on Zoom. But anyways, I just got the second pair, $17. When I buy prescription, not bifocal, just regular, with a good frame, I think they cost me all of about $20, $25 shipped to your house. The only thing I give a recommendation, you need your pupil distance, have an optometrist or an eye doctor measure that. Don't you do it. They have a device that can have you look in there and give you an exact number. All right, let's get to work. We have finished the chapter on alkenes, double bonds, and alkynes, triple bonds. This Wednesday, I will go through the alkenes and alkynes problem set. So make sure before I do, you try those problems. So, you know what that means? It's new chapter time. It's new functional group time. Yay! It's always exciting time. Let me close this. And that new chapter deals with aromatic compounds. Oh, this is going to be so exciting. But then again, I'm an organic chemist, but still. Now, what are aromatic compounds? They're named aromatic, they smell, because they originally only organic compounds isolated from spices and herbs. Example, vanillin, which you taste in vanilla extract. By the way, Dr. White's a vanilla extract freak. I love vanilla in a lot of things. Have a special part of it called an aromatic compound. And these aromatic compounds have unusual chemical properties, especially they're very stable compared to other organic molecules. And many of them, and I should say, here I have C6H6, that really should be C6H5 ring or different, an aromatic ring. Now, on a personal public service thing, I don't know if I mentioned this before or not, but in Evanston and also Chicago and a couple other places in the area, but you can order online, there's a great place called the Spice House. I've been going to them for many, many years. When I used to live closer to Chicago, I'd go there. In fact, when I've been in there, I've been introduced to some of the top chefs in Chicagoland who buy their chef spices there. Why was I introduced? Because years ago, I was in there, the one in Evanston, the owners were there, happened to be at that store. They're having trouble with a balance, being an organic chemist who knows balances. I helped them out and they were forever grateful. So whenever I'd be in there, they'd say, hello, know me, and they'd introduce me. This is some of the best spices you can buy in the United States. And this is what I buy. I have a bottle and a half in my house. It's called Madagascar Pure Double Strength Vanilla Extract. If you notice, it's quite expensive. Yes, $85 for an 8-ounce bottle, which is what I usually buy. If you've ever used this, once you do, you'll see the stuff you buy in any supermarket is total garbage. And it is. This is the best that you can buy anywhere in the United States. And this is really, really awesome. But anyways, they also have, and I'll talk later in the semester, some great regular spices. They have one that's very dangerous, but very good. It's called habanero powder. They've got 3 different types of chili, medium, mild, medium, regular, and hot chili. I get the medium. And they also have the best cumin you'll ever buy in the United States. This place is good, and they got a lot of other good stuff. But back to aromatic compounds. So aromatic compounds were isolated from herbs and spices. And what you don't know is back in the 14th, 15th, 16th, and part of the 1700s, many countries were at war over places that grew the plants that made these spices. In fact, you don't think about it, but the United States was found by Columbus. He wasn't the first one here, the Vikings were, but Columbus came here not to find the United States or America, but he was looking for a shorter route to India and that area to get spices. Why? Well, if you think about the Middle Ages, if you had a piece of meat, the next day they didn't have refrigeration, it started going bad. So you put spices on it so you could still eat it. Yeah, but anyways, they were. And that reminds me of another public service thing I can show you. I don't get any kickback from Amazon. There's a great book, and I really should order it for my tablet. It's called Napoleon's Buttons: How 17 Molecules Changed the History of the World. And the reason it's called Napoleon's Buttons is there's a tale. Nobody knows if it's true or not, but it is true. When Napoleon invaded Russia and the heavy Russian winter helped defeat him, that was his first, I think, major defeat. Don't quote me on that part, but anyways, and there's a theory. One of the reasons his army lost because the buttons in their winter coat and their uniforms were made out of a metal that in the cold became very friable. Friable is a chemical term meaning it falls apart and breaks. How are you going to fight in a winter cold if you're trying to hold your coat together because the buttons just disintegrated? This is a great book. By the end of the semester, I highly recommend it. And most of these 17 molecules are organic. Yay. And one area they talk about aromatic compounds in the war that were fought between Germany, France, England, the Netherlands, Spain, Portugal, over control of these molecules, aromatic compounds. Now, when we talk about aromatic compounds, the simplest compound is called benzene. Right now, click the switch, will this be on a test, is in the off position. Now, when we talk about benzene, one of the greatest of all organic chemists is I think this was before Germany, Austrian chemist Kekule. Now, he was the first one to propose a reasonable structure for benzene, which is the simplest of all aromatic compounds, which I'll talk about in a little while, the structure. And that alone is a lifetime achievement, but he did a few other things too. What? Well, I'll talk about his snake dream in a second. He was one of the first organic chemists, before they called chemists organic chemists, that realized carbon should have 4 bonds to it. That's called the tetravalence. So he came up, was the first to realize carbon has 4 bonds to it. That alone is a lifetime achievement. He also was one of the first to recognize that carbon atoms are connected together to form molecules. And like I said, he developed that benzene contained, and I'll explain what it means, 3 conjugated double bonds. Now, late in his life, he was at a symposium, the story goes, and someone asked him, how did you come up with the idea to that benzene structure? What is the structure of benzene? And as soon as you say Kekule to any organic chemist who knows organic chemistry, they'll say Kekule snake cream. And at the symposium or meeting, he told the people, the night before I came up with my idea, I had this dream. And in this dream, there was a snake chasing itself, and it grabbed onto its tail, and it was going in a circle. When I woke up, I remember that dream, and that gave me the solution to what's the structure of benzene. And he's famous for that dream, and also what he did. Any of these achievements, coming up with the structure of benzene, carbon has 4 bonds to it, carbon can bond to other carbons. Any one of those is a lifetime achievement. He did all of those. Now, quick thing, here's a postage stamp honoring Kekule. Love that beard. I got to keep my beard short, because if I go into a chemical plant, which sometimes I do, I've got to have it short, so if I have to put on a gas mask, I won't break the seal. And when I keep it short like this, it won't. That would break the seal. But here's a picture of Kekule. He lived from 1830, approx. 29 to 1899. Now, this postage stamp is from a country that no longer exists. DDR is Deutsches Demokratische Republik, which is otherwise known as East Germany. And this was a 25, I think, cent postage stamp with, here's the structure of benzene and his name. Now, about 4 or 5 years ago, before that, I'd always, when I showed this page, I told my students, if you see with a stamp for sale, let me know. If it's reasonable, I'll buy it. About 5 years ago, a student of my Chem 170 emailed me. And she said, go to eBay right now. They're selling the Kekule stamp. And I went there and they were selling it. And they were cheap too, so I bought a couple. They're downstairs framed in my living room. But this is Kekule. Now, the problem with benzene was organic chemists knew it had 6 carbons and 6 hydrogens, C6H6. So how do you show that in a molecule? switch is now on. Click. The stuff you should know. So here's benzene is a ring. With 6 carbons. And to have 6 hydrogens, so it exists like this. This is one way of showing it. This is called the Kekula structure. And notice each carbon of the 6 has 3 bonds to it. This is one of the rarest times, so write it down in your diary. Dr. White was actually showing hydrogens on a ring today. And notice this is the structure for benzene, which you should know. It's got a ring with 3 double bonds, and they're conjugated. Conjugated, which I'll never ask on a test, but I will use terminology, means alternating single, double bonds. And notice this is conjugated. Double bond, single bond, double bond, single bond, double bond, single bond. So it's alternating double, single, double, single, double, single. And that's the structure of benzene. Now, there's a way, or it's not a way, but benzene can exist using a Kekula structure in another resonance form. And in organic chemistry, and I'll never ask you what's resonance, but I will use the term, that's where you can draw another structure where all you move is electrons. And there are 2 resonance structures for the Kekula. If I move those electrons there, there'd be too many bonds to this carbon, so this moves there, and this moves there. And when that happens, I've not rotated it. Let's call this carbon 1, this carbon 6, 1, 6. They're different because the double bonds. And this is called resonance. And we show that by a double arrow. It's not an equilibrium, it's resonance. And it turns out the more resonance forms you can draw of something, the more stable it is. And that's a proven fact in organic chemistry. The more resonance forms, this case 2, it makes it more stable than if I couldn't draw 2. And back here, I used to put brackets. These 2, either one cannot be isolated alone. They exist at the same time. They go back and forth always. Now, I'm going to turn the switch. Will this be on a test? Click to the off position for the next couple of slides, but it's something I want to go over. Now, in a pi bond of a double bond, as I mentioned earlier, there are 2 electrons, and each one are in what's called the pi orbital. And they overlap to form a pi bond. Now, if we look at this, right here on the left are each carbon of benzene has an electron in that little hourglass. That's the p orbital. And they can all share, and they form this cloud of pi electrons. Now, we show it by double bonds between 2 carbons at a time, but it really exists like this. And if I were to look this way down at the top, it would look like that, where that circle is the pi orbital like this. Now, it turns out there are 3 ways of drawing benzene. And the switch is on for what I'm showing you now. here are my two calcula, and this is called the localized pi bond structure, delocalized structure of benzene. I will, in class, always write it this way or this way. Rarely will I use that. Why? Because I just think the first two, this one and this one, looks cooler. And Dr. White tries always to be a cool dude. But anyways, on a test, if you were to write the structure of benzene that way, I would give you full credit. Again, there are three different ways of drawing benzene. The first two are calcula. Let's call this A and B. And the delocalized pi cloud one is C. Any one of those is correct, but I'm going to always draw it A and B, usually A, because I think it looks cooler, and I try to be a cool dude. Now, switches soft for this one, but I've been told sometimes in certain entrance exams, like nursing and other stuff, I don't know if it's true because I never took them, that they ask the following question. Now, how do you know if something's aromatic? It's a cycloatomic, meaning it's in a ring and has 2n plus 2 pi conjugated electrons. And if we look at benzene, and I'll never ask this on a test, is how do you know this is aromatic? Notice each double bond has 2 pi electrons. And 2 plus 2 plus 2 is 6. 2n plus 2 equals 6. When n is equal to 2, it's true. So that tells me this is aromatic. I will never ask that on a test or the final, but I've been told some people ask those questions on entrance exams. All right, now, here's the way, and there's the third way. These are the calculus structures, the delocalized pi. If I ask you to draw the structure for benzene on a test, you can use any one of those three. And by the way, click, the switch is on. I'll never ask on a test, what kind of structure of benzene did I draw? No, but I will ask you to know how to draw the structure of benzene using any one of these three. Now, when it comes to nomenclature of aromatic compounds, it turns out, and IUPAC has done this. Remember, IUPAC means the official name, and IUPAC, which I'll never ask, stands for International Union of Pure Applied Chemistry. I just think it's cool to say that. But they came up with rules, and sometimes when they were doing this, they say, you know, organic chemists have been saying this name for eons. We're not going to get them to change. So they took the common name for this structure, which also could be drawn this way or this way. Why, it's really rare. I've done these a couple. And that's benzene. And this is the structure for benzene. It's not cyclohexatriene, which would be, you would think that IUPAC, nope. They said chemists have been calling this benzene for eons. We're not going to change them. We'll just make that the structure called benzene. And they did. So if I ask you, draw the structure for benzene, this is one. Now watch closely. If I ask, draw the structure for benzene, and this is what you drew, notice there are no double bonds. This is cyclohexane. Remember to put the double bonds in, or the circle, because without that, it's cyclohexane, and this would be wrong if I asked you to draw benzene. And unfortunately, I've had students who do that. They get upset. Well, aren't you going to give me partial credit? I said, no, you need the double bonds in there, and they're conjugated, alternating single, double, single, double. They're conjugated. Now, this is a structure of our benzene. Now, what happens when you put a methyl group on a benzene ring? You say, oh, I'll call that methylbenzene. Wrong. When you have a methyl group on benzene, again, this is a molecule that's been around eons. It's called toluene. A methyl group on benzene is called toluene. So if I ask you to draw the structure of toluene, these would be the three possible structures. The two kecular structures, you only have to do one of the three, or the delocalized pi bond, which I rarely do because I like the first two, it looks cooler. Now, sad story. Turns out benzene, which is a liquid at room temperature, and toluene, which is a liquid at room temperature, were used for many years till they've invented latex paint as a solvent in paints, among other things. Unfortunately, and also in glue. Unfortunately, if you inhale enough fumes from benzene or toluene, it destroys major parts of your body, your organs, and rots your brain out. And it's sad. And the reason why I'm saying it's sad is when I was young, I had a cousin of my mother who for a number of decades had been a painter. And throughout his career, back then, when I was a kid, they were using paint that had benzene or toluene in it. And by the time I met him, he was in his 60s. There wasn't much left going on here. He was about 2 steps above being a vegetable, and it's very sad. Now, another thing, which I'm not asking you to do or anything, and luckily I've never met in my life, but in the past, you've heard about people who sniff glue. And in glue, what they were sniffing was the toluene. And toluene, I guess, gave them some sort of high, but it also destroyed their body and their brain. And that's why you shouldn't. And for a while, they've taken it out. I don't know how many of you are familiar with liquid paper. It's the stuff you put on a piece of paper before when you used to use a typewriter and you made a mistake, you put it in there, you could type over it. When I was in college, it was a godsend. For a long time, they had toluene in it, and people were sniffing that, getting high, and also having serious health-related problems because of what it did to their brain. So on a test, if I ask, what's the name of the IUPAC name of this compound? Benzene, or to draw it, benzene. What's the IUPAC name of this compound? Toluene. A methyl group on a benzene ring is toluene. Now, for the rest of the slide, I'm going to switch off, but I thought I'd tell you this. This, when you have a vinyl group, CH2 double bond or CH double bond CH2 on a benzene ring, that has the common name styrene. Have anybody ever heard of polystyrene? Like the white insulated cups, or the real cheap lightweight coolers you can buy at various stores. Those are made of polystyrene foam. And they're called polystyrene foam because they're made from this compound. I'll talk more about that when we get into polymers. I think that's week 13 or 14, way down the road. All right. Now, before we do numbers, let's talk about some halogens and other things that I haven't talked about. If I were to have this molecule, what would it be called? Good question. Well, here I have a benzene ring. And when it's mono-substituted, only one substitution on a ring, you don't need a number. And a halogen chlorine is called chloro. So that would be chlorobenzene. If it was a bromine there, it would be bromobenzene. If it's iodine, iodo, F, fluorine. Now, there's a new functional group or substituent that I talk about, NO2. And the bond from the ring is to the nitrogen, and the nitrogen has two oxygens on it. Again, the bond is from the nitrogen to the ring, and the nitrogen has two oxygen, NO2, that's called the nitro group. And this is called nitrobenzene. And it turns out nitro groups play an important role in organic chemistry and your daily life. Now, I have here sulfonic, and I'm not going to hold you responsible for that, even though I will talk about it later this chapter. So I just mentioned it, SO3H, where the sulfur is bonded to the ring, is called a sulfonic or sulfonic acid group. But these you should know now. Cl is chloro, Br is bromo group, and if it's on an alkane too, like it would be one bromo butane. F is fluoro, NO2 is nitro. This you don't have to know. So this is a chart you should take time to memorize. Cl is chlorine or chloro. Bromine, Br is bromo. Iodine is iodo. F, fluorine is fluoro group. And NO2 is a nitro group. Now, in IUPAC, you use numbers when you have two or more groups, but in organic chemistry, what I like you to learn that people use, and Dr. White uses on a test, is the following: di-substituted. Come on. And hang in there. This will take me a little while to finish. If we were face to face, you'd be watching me write this on a whiteboard, just like I'm doing now. Sorry, I'm having a bad ring drawing day. Now, let's look at this first compound right here. I have a benzene ring. Over here, I have an ethyl. Over here, I have an N-propyl. And this one, I have an ethyl, an N-propyl, benzene. Remember, a ring with 3 conjugated double bonds, alternating single, double, is called a benzene ring. And finally, the last one, I also have ethyl and propyl benzene. Now, notice here, this is 1,2 disubstituted, carbon 1, carbon 2, 1, 2, 3. 1,3 disubstituted, 1, 2, 3, 4. 1, 4. And organic chemists use the following. Dr. White's being subtle, hint, know this. And if we look at this, 1, 2 disubstituted, it's called ortho. So this first one, I'll call 1, 2, 3, is ortho ethyl and propyl benzene. Number 2 is 1, 3 disubstituted, which is called meta ethyl and propyl benzene. And number 3 is 1, 4 disubstituted, and we call that para. So number 1, the IUPAC name is orthoethyl and propyl benzene. Number 2, it's 1, 3 disubstituted. That's meta ethyl and propyl benzene. And number 3 is 1, 4 disubstituted, which is para. So that's para ethyl and propyl benzene. And you should know the ortho, meta, and para. Now, listen carefully. Common mistake students make on test number 1, they use ortho, meta, and para for cyclohexane. No, this ortho, meta, and para, I don't know how it evolved. I looked one day, I'll have to look again when I have time to look on the internet. Is exclusively used for benzene rings. That's the only place. How it evolved, don't know. Sort of like, why did someone decide to call this benzene? I don't know. Why is that called a door or this a wall? I don't know. Why don't we call this a door and that thing a wall? Someone decided. Well, someone decided, and organic chemists still do it for benzene. Ortho, meta, para. Ortho, 1, 2 disubstituted. Meta, 1, 3 disubstituted. And para, 1, 4. You name one of the 2 groups, and it's only for disubstituted. One is on, like here, carbon 1, and the next carbon is on, the other is on 2. Here it's on 1, and the other is 3. And finally here it's on 1, and the other is on carbon 4 of the ring. And 1,2 disubstitute is meta. 1,3 sorry about that. Let's wind this back up and say it again. Norp. I just wanted to say it back. 1,2 is ortho. 1,3 meta. 1,4 para. And the question would be, give the IUPAC name for this, 3 points each. What do I look for? What's different? Oh, I've got a ring with 3 conjugated double bonds. That's benzene. That's my root name. I have an ethyl group. And now I'm going to be a lazy organic chemist. I'm no longer going to call this a tert-butyl. I'll call it T-butyl. You can do either one, a T-butyl group. So I have T-butyl, ethyl, benzene. Notice the ethyl group is on carbon 1, or I could say the T-butyl group is carbon 1. Doesn't matter what you say. If I count, 1 is on carbon 1, in this case, the ethyl, and T-butyl is on 4. And if we look up here, oh, someone was nice enough to draw this nice table. 1,4 disubstituted benzene ring is para. So this would be para T-butyl ethyl benzene. Now, if you remember, I am not holding you to the alphabet rule for substituents. So if you had written down para ethyl T-butyl or tert-butyl benzene, I would have marked it correct also. So we have 1,4 disubstituted benzene. We use ortho, meta, and para. 1,4 is para. And this would be para T-butyl or tert-butyl ethyl benzene. And that's how you do it. Oh, I got time for one more thing. You don't have to write this down. Everybody know what this is, and you don't have to write it down. Time's up. It's para 1,4 medic. Medic, para 1,4. It's a chemistry joke. And with that, I'm going to say it's time for a 5-minute break. I'll see you in 5 minutes. Time to get back to work. And we're talking about aromatic compounds. Now, I should tell you, and we'll talk more about it when we get into other functional groups. The next time you smell some cinnamon, by the way, I love cinnamon. My older sister hates it with a passion. But anyways, you're smelling an aromatic compound. The next time you're smelling raspberries, you're smelling aromatic compound. And the next time you're smelling my favorite vanilla extract or vanilla beans, you're smelling an aromatic compound. And it's just amazing the different things. Same thing with cloves. The next time you smell some cloves, you're smelling an aromatic compound, which makes me remember this. Whenever I smell cloves, I think of a dentist's office. What, a dentist's office? Well, for many years, dentists, if they were good ones, and I've had some good ones, I have some not, so I've got a really good one now in Palatine, Dr. Angerain. You need a good dentist, let me know. I'll send you his contact information. And he's a young guy, and he's one of the best in the state. And being young means he's going to be around a while. I had one dentist who was really great, one of the best in the United States. Unfortunately, years ago, after a heart attack and other illnesses, he passed away. Well, anyways, if you have a good dentist, the old days, before they injected you, ouch, to deaden your nerves, they'd rub this liquid on your gum to sort of desensitize it to the needle. Ouch. But anyways, what were they rubbing on there that numbed your gum? Oil of cloves. Why does that chemical aromatic compound do that to your gums? Don't know. That's not my area. I know the structure. We'll talk more about it in the lab. We'll do. All right, let's get back to nomenclature of organic molecules, of aromatic molecules. And don't forget, this is benzene. And when you have a disubstituted, we use ortho, meta, and para. Ortho, 1,2 disubstituted, meta, 1,3, para, 1,4. And, well, I can do it by bad joke again. This is paramedic, 1,4 disubstituted medic. Never mind. And the question is, give the IUPAC name for the following. Your turn. And here's a little table that will help you, that you should know. Now, hopefully by now you've learned your alkyl groups from key alkyl groups folder. And while you're doing that, I'll do this. One thing I should ask in the future, I tried to eliminate choice too. When I ask, are you done? Just put down yes, and when you're finished, if you're not, put down yes again. That way I can tell when everybody's done, because I don't think there's a way you can re-vote when I do that, is there? I don't think so. So just put down yes when you're done. If you're not, wait until you're done to put down yes. And that helps me. Well, it looks like everybody's done, so I better get to work. What do I see that's different? Ooh, a ring with 3 conjugated double bonds, alternating single, double, single, double, single, double. I like those fancy hand signs. Well, anyways, that's a benzene ring. Then I have an N-butyl and an isopropyl. And on a benzene ring that's di-substituted, you should use this table. This is on carbon 1. I could have said that's carbon 1, that's 2, that's 3. So this is a 1, 3 di-substituted, which means this is meta. So that'd be meta N-butyl isopropyl benzene. Now, if you put down meta isopropyl N-butyl benzene, I would still give you full credit, even though remember prefix N and iso are ignored. This is B, this is P, but if you did it the other way, I'd still give you full credit. All right, let's look at the following. What would be the IUPAC name for that molecule? And I was just looking at the clock, and I'm also over here. I have a clock with an electronic calendar, and we're on track. Yay. I tell you, one of my hobbies is model railroading. I use N gauge and G gauge, getting back to it. When I was a little boy, about 6 or 7, sometimes on a Sunday when my father had the time, he'd take me down. My sister, we took one, she didn't like it, so he only took me. And we go to the south side of Chicago back then, and they had the master train repair and train center. And we'd spend Sunday morning standing at the fence, watching him bring these huge engines. Back then they were steam engines, behemoths, onto a turntable, turn them around, fix them, and do all sorts, park them. And he and I would just stand there, just totally enjoying ourselves. All right. But anyways, back to this. I got sidetracked. But anyways, what's the IUPAC name? 6-membered ring, 3 double bonds conjugated, benzene. I've got a bromine on there. Oh, someone was nice enough to put this table. Benzene with a BR or a BR on anything is called a bromo group. Now, when there's only one substituent, you need no numbers. If you put a 1 there, I would have taken off points because any position is 1, and therefore I'm done. Bromobenzene. Here's one more for you to do. And let me remind you, 1, 2 is, or I'll rewrite it. We're in class, in a classroom. I'd have this table and this one on the whiteboard so you could look at it. But these are things you need to memorize. Oops. And don't forget, test number 1 is not this Wednesday. It's been postponed 1 week. I've sent out email announcement. Hopefully you're all reading your emails, student emails, on a regular basis. Remember, I read mine twice a day, but my day starts early. I think this morning I got up late. I slept in real late, so I read my emails about 7:30 or so. All right, let me do this. Don't forget to vote. And everybody's done, so I can get to work. What do we have here? Ooh, 6-membered ring with 3 alternating double bonds, single, double, single, double, single, double. That's a benzene ring. Ooh, I've got an ethyl group here. What's NO2? And NO2 is a nitro group. So this would be ethyl, nitro, benzene. Now, it's disubstituted 1,4. 1,4 is para. So that'd be para ethyl nitrobenzene. And that's how you do it. Now, an interesting thing is this. This is toluene. And if I draw the structure, ask you, draw the structure of toluene, that's the IUPAC name. Now, what is interesting, if we look at this molecule, now, even though CH3 on a benzene ring is toluene, it's still considered disubstituted, where the methyl group is 1, and here I have a chloro group on 2. So how do we name that? It'd be chloro, but CH3 on a benzene ring is called toluene, so this is called chlorotoluene. Now we're not done, because the chlorine could be at many places on that ring. And notice it's 1,2 disubstituted. If we come up here, up, hold on. Once again, I've got so many things open on my computers. I've got to do this because Word gets confused. All right, we're back. I apologize, but even though I've got a fast computer with my tablet mouse and Word open and Zoom, it says, I'm going to burp, and I have to close the Word, and it clears out some temporary files, and I'm back to. So we're looking at this. CH3 on a benzene ring is toluene. With the chlorine, it's chlorotoluene, but it's disubstituted. Notice 1, 2 would be ortho. So this would be orthochlorotoluene. Even though toluene implies or tells you CH3 in a benzene ring, chlorotoluene is still disubstituted. And that's why we need this. And so I better give you one to try. And there you go. Question is, give the IUPAC name for the following. And just to remind you, BR is bromo, 1, 2 ortho, 1, 3 meta, 1, 4 para. Remember, when I send out a poll, if you're done, say yes. If you're not, pull off until you're done for saying yes, please. And remember, I try and give everybody time to finish, so please be patient. All right, I think everybody's done. So if we look at this molecule, oh, look, a ring with 3 double bonds that are conjugated, alternating single, double, single, double, single, double. That's a benzene ring, but I have a methyl group on it, and that's toluene. And I have Br. Br is bromo group. So it's bromotoluene. Notice Br, bromo, and you should learn this table. And 1,4 disubstituted is para. Notice this is on carbon 1, 2, 3, 4. So it's 1,4 disubstituted. So that would be para. And that's how you do ortho, para, and meta. And you should also know the new groups I've talked about. These are just called substituents because they're not alkyl. Our chlorine is called a chloro, Br bromo, iodine iodo, F fluoro. Sometimes I get the O and U mixed up. That's a bad spelling error I do. And NO2 nitro. Now, when you have more than one group on there, or 2 groups, I mean, on a benzene ring, then we use numbers. And let me remind you about something I talked about earlier, not this chapter. So when you have two of the same thing on somewhere, we call it di, 3 is tri, 4 is tetra. And if you notice this molecule, I have a benzene ring. I have not 1, not 2, but 3. So this would be tribromo. And this would be in position 1. This is 2. This is 3. When you see tri, that means you need 3 numbers. And that would be your 1, 2, 3 tribromobenzene. And here's one for you to try. Give the IUPAC name for the following. And don't forget, on Wednesday, I'll go through the alkenes, alkynes problem set. So I highly, highly recommend that you try it before I do. Remember, di is 2 groups, tri is 3, tetra is 4. And by the way, Cl is chloral. And it looks like everybody's done. So it's my turn. And if we look at here, oh, I've got a benzene ring. And I have not 1, 2, 3 chlorines. I start this way, 1, 2, 3, 4, 5. So it's trichloro, benzene, and they're on carbon 1, 3, 5. Now, let me show you when you have toluene. And I'll do this one. Here we have methyl group on a benzene ring. That's toluene. And NO2 is a nitro group, and there are 3 of them. So that would be trinitro toluene. This is on carbon 1. When in this case, the methyl group is 1. This is 2, 3, 4, 5, 6. So try 3. I need 3 numbers. 2, 4, 6, trinitrotoluene. And that's how you do it. 2, 4, 6, trinitrotoluene. 2, 4, 6, trinitrotoluene. Boy, my jaw's getting tired. I tell you how lazy organic chemists are. 2, 4, 6, trinitrotoluene. Well, I'm going to call this a common name, and I'll call it TNT. And that's the active ingredient in dynamite. And it's 2,4,6-trinitrotoluene. Now, 2,4,6-trinitrotoluene, otherwise known as TNT, is a liquid at room temperature. And it's very shock sensitive. If this were TNT, thank God it's not to bring religion into the classroom. If I were to go like this a couple of times, I'd be dead now and my house would be gone because it's that shock sensitive, it could blow up. Luckily, I've never worked with TNT. Now, it turns out a very important pair of brothers did, and they found a way of making it safe by mixing it with certain clays to make what we now call dynamite. And who are those brothers? The Nobel brothers, Alfred Nobel, and I can't remember his brother's name. How many of you have heard of the Nobel Prize? Well, that was Alfred Nobel. Now, where did he get all that money to set up the Nobel Prize Foundation? Well, it turned out by making explosives safe, it was used for mining dynamite, but most of it was used to make explosives for militaries of the world. And by doing that, they made a lot of money. Now, sad part of the story is it was still dangerous, and even today it's still dangerous to make explosives from TNT and also trinitroglycerin. I'll talk about that later in the semester. And unfortunately, one of the plants of the Nobel brothers blew up, and Alfred Nobel's brother also died in there. And it's sad, it was dangerous. But next time you think about the Nobel Prizes, chemistry, medicine, peace, I think there's one in literature. Those are all funded originally from money obtained from selling chemicals that are used for war. Nothing wrong with that in the sense that it's just a fact of life. All right, there are two types of nomenclature questions. And the second type is, oops, wrong color. Right color. I'll let you try this right off the bat. I'm gonna let you have fun from the start. Draw the structure for benzene. And while you're doing that, I'm gonna go blow my nose. I'll be right back. As promised, I'm back. All right, I think everybody's done. So benzene, you should know the structure is this calculus structure, or you could have drawn this one, or, which after today, you're not going to see me doing this often, this would also be accepted. If you drew this, this is cyclohexane. It's important to put stuff in the ring, as you see here. And why don't you try this one? Draw the structure for Parrott's nitrotoluene. Your turn. All right, I think everybody's done. So how do you know how to decode this? As with all organic chemicals, names, you start from the right, move left. Toluene. Remember, that's a benzene ring with a methyl group. And don't forget the double bonds that are circle inside. Nitro is N2. Here it tells me it's 1,4 disubstituted. 1, 2, 3, 4. And that would be this. If I rotate it 180 degrees, and I usually don't, I try and write it in a way most of you would do it, but this would be also acceptable. And you could rotate it other ways, but both are para-nitrotoluene. And let's do one more. Draw the structure for 2,3-dichloro. Remember, chloro is Cl. Toluene. Your turn. All right, my turn. We start here. How do we decode this? You start from the right, move left. Toluene. Methyl group on a benzene ring. Don't forget to put the bonds in there in the ring. Otherwise, it's cyclohexane and it's wrong. I had a student lose 10 points on nomenclature problems in a test because that student didn't put this. This, which is cyclohexane. All right, next, chloro is chlorine. Di means two. And there, this is carbon 1, 2, 3. And each one of those has a chlorine. And that's how you do nomenclature. I have to open something. Now, aromatic compounds are very stable compounds. Why? If you see on your screen, see how the pi electrons are there? That makes it very stable. How many of you ever played Ring Around the Rosie? Holding hands, going around in a circle. But anyways, these are holding hands, electrons. And that makes it very stable. If you break one of the pi bonds, it loses that stability. Now, switches off. Everybody see resonance energy of benzene on your slide on the screen? Thank you. Switches off. Now, there's something called resonance energy, and that's the older name. They also call it stabilization energy. Turns out benzene is very, very hard to hydrogenate to double bonds compared to, say, cyclohexane, where you have one double bond. It doesn't react like it has three separate double bonds. It doesn't. There's something different in benzene, and it's true about all aromatic compounds. And what's that difference? That's called stabilization or resonance energy. I like the older name resonance. And that's the difference between the energy of a real molecule and the calculated energy for the most contributing structures. So if you looked at benzene, if you were to take the energy of cyclohexane plus three double bonds, you get a number. And if you look at the actual measured number of the energy of benzene, it's much lower, more stable. And that's because aromatic compounds are more stable than similar non-aromatic, and that's due to the resonance energy. Those holding hands of the pi electrons gives it a tremendous amount of stability. And because of that, when you do a reaction with an aromatic compound, you don't break, very rarely, the double bonds. You do what's called electrophilic aromatic substitution. Switch is still off. Click on this slide. I'll be turning it on in a little while. And, ooh, big words there. Electrophilic substitution. Well, substitution is when I take one thing and replace it with something else. What about electrophilic? Well, electro, that means negative electrons. What's the, not prefix, philic mean? I got a brain freeze. But anyways, phile means lover. I'm an audiophile. I love music. I also have 5 stereos in my house, and some of them are really good, like all of them. I actually have one in my garage. So if I'm out there working, I can listen to music. And if you look on the website, I have some of Dr. White's favorite music. My claim to fame, I saw Jimi Hendrix live. I saw the Moody Blues live. If you don't know what I do, those groups, look on YouTube. So electrophilic means electron loving. Aromatic ring, substitution, you're changing something, replacing it. And due to resonance stabilization, they don't undergo addition reactions easily, really not at all, almost not at all. And aromatic compounds undergo substitution. And these are chemical reactions where the hydrogen atom on the aromatic carbon of the ring is substituted for another atom or group of atoms. All right, click, the switch is on. How many of you ever seen the movie, This is Spinal Tap? It's a cult movie. There's one part of it where it's about a band, this strange movie. And I don't know, lead guitarist, I think it was, says, we're so good, our amps only go up to 10, but we actually turn them up to 20. We're that loud. So, switch is on, and I've just turned that dial up to 20. Let's talk about halogenation. If you take a benzene ring, react with halogen, in real life is chlorine or bromine, and you need a catalyst, ferric trihalide, you form this new compound where you replace one of the hydrogens on the benzene ring with a halogen. Now, you also form HX, HCl, or HBr. That's inorganic. I'm only interested in the organic stuff. So, if I were to ask, give the organic products and notice I say organic. And if here's the one, how do we do this? Oh, we've got a benzene ring. Ooh, chlorine, that's F. And I have a catalyst, notice ferric chloride, FeXL3, X3, and that can be chlorine or bromine. And what happens is, remember, you still have the double bonds conjugated in the benzene ring. I replace one of the hydrogens with a halogen. In this case, what's X? It's chlorine. So what you make, don't forget the double bonds. If you don't, that's cyclohexane, and I mark it wrong. In fact, let me show you. You need the bonds in there because this is chlorocyclohexane, which is different compound from chlorobenzene, way different. And that's how you do it. You don't lose these double bonds in here. These stay. Now, if you put a circle, you could have done that too. Either way is correct for me. All right, your turn. And why don't you try this one? What would be the product, organic product or products for the following reaction? And don't forget the 2, Dr. White. All right, I gotta get going because we're almost out of time. Time flies when you're having fun with aromatic compounds and Dr. White. And if we look at this, we have a benzene ring reacting with halogen gas and ferric trihalide catalyst. X can be chlorine or bromine. And therefore we have our benzene ring. And we replace one of the hydrogens with bromine. And we're done. We made bromobenzene. Speaking about done, I'm done. All right, remember, on Wednesday, I will be going through the alkynes and alkenes problem set. I highly recommend that you do them before I do, and that way you can ask questions. Don't forget, tomorrow night, late evening or night, from 6 to 7:15, of my office hour. If you have any questions, come on by. Don't forget the lab we did last Wednesday is due tomorrow by the end of the day. All you have to do is answer the questions. And don't forget, test one has been postponed by 1 week. With that, I'll say in Yiddish, meaning go in hell, and still nasty out there in certain places. Pandemic really isn't over in my mind, but I'll say gang gesund. Bye now. I stole that from Granny to Beverly Hillbillies.